We're going to look at making predictions in acid-base reactions, which is really essentially what all do we need to be able to do beyond drawing a mechanism with this acid-base chemistry. Now, if we think back to the ideas that were introduced in the introduction, we'll practice with writing in the organic chemistry style. Practice with writing reactions in the organic chemistry style. We'll have a chance to practice mechanisms, but we're really going to focus on predicting reactions, which is going to be what products are formed, which part of the starting material or which hydrogen in the starting material is given up, and what part of a starting material grabs that hydrogen. We're also going to predict are these reverse favored or forward favored equilibria, both in terms of the acid-base strength factors, those 5 different factors including electronegativity and size and so on and so forth that we talked about in the acid-base strength videos. And we'll also look at the calculations that are involved. So we've got a lot going on here, and we're going to do it in the context of several examples. So this video will include the first example, and then we'll look at different situations that we have to deal with in subsequent examples. And let's take a look at the reaction between acetic acid, which in chemical principles you may have written as C2H4O2, or an organic we'll write as CH3CO2H, and we'll react that with sodium hydroxide, which hopefully you remember is NaOH, and you also remember something about the acid-base properties there. So let's do 2 things. See if you can draw the dot structures for both of those materials, and let's see if you can make or predict products of those reactions. Take a few minutes, see what you can do. Now I've rearranged things on the screen a little bit to make some room. Hopefully you notice that acetic acid has the word acid in the name, and that you remember from chemical principles that sodium hydroxide is a strong base. And so that means we know that our acetic acid is going to donate 1 of its 4 hydrogens, and the sodium hydroxide is going to pick up that hydrogen. Now, we could go ahead and write what we would presumably write for chemical principles, which would be CH3CO2 minus and water. And we hopefully remember that we pair off the sodium, the positively charged sodium, with the negatively charged species in the product. Perhaps you got that prediction, perhaps not. Let's take a look at the dot structures for sodium hydroxide. First of all, you remember hydroxide is OH minus. However you arrive at this structure, whether it's through doing calculations, strictly memory, or pattern recognition, we basically want a negatively charged oxygen, and we have the sodium floating around in solution as well. Now notice we've drawn a covalent bond between the oxygen and the hydrogen. We have an ionic bond between the sodium and the oxygen because those 2 are an ion pair, 1's plus, 1's minus, and that there's no line in between the 2. Now for acetic acid, we can use this structural formula format to help us recognize that there are 3 hydrogens on the first carbon, and that the 4th hydrogen is actually on one of the oxygens. Now hopefully we'll recognize this as a carboxylic acid functional group. And that whenever we see that CO2H in a molecule, we're going to have this configuration of atoms, a carbon double bonded to one oxygen, single bonded to another oxygen that has a hydrogen attached. And now we have a decision to make in terms of which hydrogen our base is going to pick up, and we have 4 options. Now we can see that we've pulled the hydrogen off the oxygen, and so we need to think about why that is. But first, go ahead and see if you can draw the mechanism for how the sodium hydroxide grabs this hydrogen from the acetic acid. And then we'll come back and talk about making predictions as to which hydrogen, why in fact it's that hydrogen, and how to predict which hydrogen we're thinking about. So we know we're going to form a bond between the hydroxide oxygen and that acidic hydrogen, the one that's exchanged. We're going to break that oxygen-hydrogen bond away from the acid. That's going to give us a product where we have 3 hydrogens still on our carbon. We still, of course, have the basic carbon framework. We have the oxygens present on the carboxylic acid carbonyl carbon. And now that we have an oxygen here that is bonding like it's more electronegative neighbors, the halogens, or we can think 1 bond, 3 lone pairs, that's like hydroxide, it needs a negative formal charge. We've transferred our acidic hydrogen, we'll circle that to keep track of it, to the hydroxide, and we've used up a lone pair on hydroxide in the process. So we've predicted our products, having guessed that it would be this hydrogen. Now let's look at a couple of factors here. First, we assumed that we're picking the hydrogen off of the oxygen and not one of the 3 hydrogens off the carbon. We're going to just stick with that assumption for now. Let's see if we can predict whether this equilibrium would be forward or reverse favored. Now, in doing so, what we want to do is to compare the relative strengths of the 2 acids or the 2 bases in the equation. So let's start by, first of all, making sure we keep track of all of those. Let's label the acid, the base, the conjugate acid, and the conjugate base. Acetic acid, of course, is the acid. Hydroxide is the base. Remember, the acid turns into the conjugate base, and the base turns into the conjugate acid. And that may seem a little weird and counterintuitive, but if you think about it, you're exchanging a hydrogen. The acid starts with the hydrogen. It has the ability to be an acid because it has the hydrogen. It gives up that hydrogen, which means it has a place it can accept a hydrogen, and so it turns into a base. The base picks up an extra hydrogen, which means now it has an extra hydrogen to give away, so it turns into an acid. And what we want to do is look at 2 species that are going to be reasonable to compare. And in this case, the best comparison is going to be between the base and the conjugate base. And we're going to think about the stability of those. And remember, we're doing this to think about the equilibrium. Is this going to favor a forward reaction or a reverse reaction? And we think about stability comparison. We're picking the charged species because we're thinking about stability primarily of charge. It's on oxygens in either case, so we're not thinking about different elements. What's the defining factor? What's the difference between those two in terms of stability? The acetate has resonance. which means that we can delocalize or spread out that charge to a second structure. Two oxygens are helping bear the burden of the negative charge, and that makes it much more stable than a single oxygen bearing the charge, as we have in the case of hydroxide. And that makes acetate, and you may remember from chemical principles, hopefully do, that acetate is a weak base. So we've established then that the conjugate base is the more stable, and we think about the direction of the equilibrium, it's going to favor the reaction that produces the more stable product. So because the conjugate base, or the acetate, is more stable than the hydroxide, then the equilibrium is going to tend to shift to the more stable side. Another way to think about it is you have a strong base and a weak base that are fighting to see who's going to act like the base. And for better and for worse, the strong one is going to have its way, which means that the weak shall inherit the equilibrium. So at equilibrium, the strong base will have pushed off or grabbed the hydrogen from the acid, and the weak base will be the species that we see the most of, which is consistent with the fact that it's more stable, right? And we want to tend to form the more stable species in chemical reactions, at least to predict those, is what we're going to see more of at equilibrium. So at this stage, we have predicted that in terms of a qualitative terms, we're predicting that we have a forward favored reaction. And we can think of this as a qualitative assessment. And a lot of organic chemistry is qualitative. It's very hand-wavy, and oh, this one is more happy than that one, and we just like that better, and it's prettier, or whatever. We can also go back to what we learned in chemical principles about equilibrium equations and predict quantitatively, or using math, which is going to be the favored position at equilibrium. So let's clear out some space and do that. So in order to make a quantitative or numbers-based prediction, we're going to need the pKa values or Ka values of our acids. And the pKa for acetic acid is generally the case for carboxylic acids. This is about 4.7. The pKa for water is, depending on whether it's an aqueous media or not, but we'll just say it's about 16. Now, if you're wondering where do I find, there's a nice table in your textbook on pages 33 to 35. It's a 3-page table, so it's got a lot of information in there. And if you're wondering whether you need to memorize those values, the answer is no. We're not looking to memorize any pKa values. If you need any of these, I'll give them to you. But I do want you to be able to remember what to do with them, as well as why they're important. Now, one thing to remember is that when considering pKa values, the lower the pKa is going to mean the larger the Ka, and both of those mean a stronger acid, because they mean a more favored equilibrium. So a Ka, remember, is for the equation of the acid with its hydrogen breaking up into the base, or the conjugate base, and an H+. Right? So if we write the equilibrium expression for that, which is something we want to be able to remember how to do, then it's products over reactants. And the more favored the products are, the higher the concentration of these, the larger the Ka. The pKa is the negative log of that, so the bigger the Ka, the smaller the pKa value will be. So on that basis alone, we can say that because the pKa of our acid is less than the pKa of our conjugate acid, therefore we're going to have a forward favored equilibrium. We can also use a little equation, which is that the Keq is the Ka. The Keq is the Ka of the acid, or the reactant acid, over the Ka of the conjugate acid, or the acid in the product. Now it's a little counterintuitive because it's starting material or reactant over product. We're used to thinking of product over reactants, but if we derive the equation, we'll find it makes sense. We'll skip that for now. But what this shows us is that if we're going to plug in our Ka values, what we actually have is pKa value. We need to be able to interconvert between pKa and Ka. So another thing we need to be able to calculate is, given Ka, we want to go to pKa. Given pKa, we need to go to Ka. And remember that Ka is 10 to the negative pKa. And the pKa is the negative log of the Ka. So what that means is our equilibrium constant is our Ka of our acid, which is our acetic acid, so 10 to the 4.7 divided by 10 to the 16th for our product acid. So we have, if we simplify that, and we want to be able to either plug that into a calculator or work it out longhand, is 10 to the 16 minus 4.7, or 10 to the, what would that be? About 11.3. And that is much, much greater than 1. So we are a very much forward favored reaction in this case. So in summary, we are predicting equilibrium positions, we're predicting products, and we're drawing mechanisms to show how it all happens.